is again to be recorded. Okay, done. Okay, good evening once again. So we are moving on to the session 8 of day 4. And now for this session we have Dr. Ankur from IIIT Una. So before we start, he's already there. Before we start, let me give you a very brief intro. So Dr. Ankur Kumar is working as an assistant professor in the School of Electronics at IIIT Una, Himachal Pradesh. He received his Doctor of Philosophy PhD degree in Department of Electronics and Communication from MNIT Allahabad and MTech also from the same institute, that is MNIT Allahabad. He received his BTech in Electronics and Communication from UPTU, and he has published more than 25 research papers in international journals, conferences, and as book chapters. His current research interest focuses on low power VLSI circuit designs, high speed, low power analog and mixed signal processing circuits, and applications of AI and ML in these mentioned areas. So with this brief intro, I welcome Dr. Ankur. Now I hand over the session to you. Please share your screen and you are good to go.
Thank you so much for the nice introduction. So I welcome all of you. Sharing my screen. Is it visible?
Yes, your screen is visible. You can go to your PPT.
Okay, sir. Yeah, sir. So now it's visible?
Yes, it's fine. Perfectly fine.
Okay. So once again, good evening to all of you. So actually, I'm presenting today AI enhanced wide fan-in domino or logic circuits and its application for biomedical. So, Ankur Kumar, assistant professor at the School of Electronics and Triple as sir introduced myself. So I'm presenting this topic, and this topic combines two powerful fields, VLSI design and the AI artificial intelligence. Both are the emerging field, so that's why I'm also moving toward the use of the AI in the low power VLSI circuit. So actually, my area was the low power VLSI design circuits. So now, because AI is the most powerful tool and the most emerging area, so that's why we are moving toward the use of AI to design our wide fan-in domino or logic circuits so that it can be better and it can be optimized easily through the AI. So that is the motive of our presentation. So it is basically to improve the efficiency and reliability of the design circuit so that it can be improve or enhance the performance of the wide fan-in domino or circuit. So here all the road map of my presentation. So we begin with an introduction and fundamental of VLSI design and discuss the importance of low power. Then review technology and scaling why we require the scaling and what is the limitation of the scaling. And then we will study about the power dissipation and its types and more into the low power VLSI techniques. Then different design techniques of domino logic. And finally, we will focus on the domino logic and how AI/ML techniques enhance their design and ending with the application. And the last one is the reference. So the three main concern in VLSI designs are area, speed, and power. Whenever we heard about low power VLSI design, and what is the low power? Actually, in today's scenarios, if we are getting our power in the microwatt or less than the microwatt, so that means that circuits can be categorized into the low power VLSI circuits. So in modern systems, especially portable one like laptops and mobile phones, these are the power efficiency. So the power efficiency is becoming and the most critical factor. So to cater the requirement of consumer like laptops, cell phones, PDS, so we require the low power VLSI circuits. So these requirement of the customer, it can be catered through the design of the low power circuits. So as the technology is moving toward the smaller, faster, and cheaper computing system, so to achieve all these things, it can be possible only through the low power VLSI design. This has been facilitated by, as discussed, exponential increase in device density and operating frequency through VLSI technology scaling. So scaling is the most powerful tools in the VLSI. First, we focus on the scaling. We scale down our devices so that we can achieve easily. But there are some limitation when we do the scaling. So that can be avoided and that can be removed through there are so many various techniques. And in this, we are using also AI so that we can improve the performance of the system. So this has led to power dissipation as that has reached limits of reliability and cost. So in addition, continuous scaling, as we discussed, we will do the continuous scaling, but there are so many issues as this robustness issues, and because of the robustness issues, soft error signal integrity and process variability. Process variability most challenging thing in the low power VLSI design. We have to be make the robust and reliable against the process, against the voltage, against the temperature. We have to make the system are reliable. So it can be covered. So next, as topic is wide fan in old logic domino circuits. Why we are using the wide fan on logic domino circuit? Because it can be used to design a various type of register files, flash memory, programmable logic array, tag comparator, and there are so many devices that can be designed using the wide fan in old logic domino circuits. So wide fan or logic domino circuits is a core block of such system and thereby affects the overall performance. Actually, in if you are designing a system, so you require more than 100 wide fan in all logic domino circuits. If you are improving a single wide fan in all logic domain, that means you are improving the total performance in the multiplication. In the multiplication, so that means it may be so it improves overall performance in terms of power density, reliability, noise margin, and the figure of merit. The overall performance of the system will be improved in a multiplication or in a by a large quantity. So that's why first we design a single wide fan in old logic domain circuit which will be robust and low power, and it will provide the high speed also, so that we can achieve all these things through the design of the wide fan in logic, and so that we can improve the performance of all over of the system. So now AI ML in the VLSI. Artificial intelligence and machine learning are transforming how we design circuits. Traditionally, circuit optimization is a manual and time-consuming process. When we are size each transistor, first we size the transistor, then we calculate the power, delay, and other performance parameters. Then the power delay product, if you are reducing the power, then the delay may be increased, or other factor may be increased, or other factor may be decreased, or the performance of the system may be reduce. So if we are focusing on the power, delay may be increased. If we are focusing on the delay by changing the size of the transistor, so that is the very challenging in the traditional method. So with AI and ML, we can now automatically predict and optimize performance parameter like power, noise, and delay. and we size the transistor using the AI and ML. This is especially beneficial for biomedical electronics where devices need to be ultra low power and highly reliable. So in that field, we can use AI/ML very efficiently. And there are so many studies in which it has been shown that AI enhance based circuits, low power circuits, achieve around 15 to 25% reduction in the power and around 10 to 15% or more than around 20% increment the speed and around 10 to 20% better noise immunity compared to the traditional method if we use the AI. So that's why the use of the AI/ML is very important to design any circuits. So what are the performance parameter of VLSI design? So to compare the performance, there are some important performance parameter. There are another parameter, but when we are design wide fan or domino circuits, so we require these type mainly these performance parameter, in which first one is a power dissipation, and in the power dissipation mostly there are two parameters switching power dissipation. We easily can say it as a total dynamic power dissipation, and another one is a leakage power dissipation. And it has there are so many components of the leakage power dissipation. But when we are going to design a wide fan or logic domino circuits, so we simply focus on the uh, subthreshold leakage current, which is the most among the most important parameter in the designing of the wide fan or logic domino circuits. Next one is the noise immunity. How much noise, how much immune our system uh, against the noise. And next one is a figure of merit. It is basically calculated based on some particular formula in which we use the power dissipation, gain, area, and so many factors, so that we calculate overall figure of merit. That overall, if overall figure of merit is increasing, that means we can say our circuit is reliable, and it can be uh, improve the performance of the circuit. So third one is a delay and power variability. Because of the variation in the when we are fabricating our circuits, so during the fabrication, it is not possible to achieve exact transistor size. Whatever we use to design or simulate our circuit, it is not possible to fabricate on the same size. So there are some mismatch. So because of this mismatch, a variation may be occur in the delay and the power variability. And next one is a propagation delay. It is basically is the speed. So we can focus. We will also focus on the propagation delay. And last one is a area. Basically, in the digital circuits, we are just calculating area at the initial level, how many transistor we are using, in which the size of the PMOS is counted as a two times of the NMOS. And when we are designing the layout, so basically we are calculating the area in terms of the layout. So first one is the introduction to VLSI design. This is the based on the transistor count. If the transistor count in a single chip is around 1 to 100, so it can be categorized as the SSI. We can say the a small scale integration. If the transistor count is around 100 to the 1000, so we can categorize in the medium scale integration. If the transistor count is 10 की power 3 to 10 की power 5, so we can categorize in the LSI, large scale integration. If the transistor count is 10 की power 5 to 10 की 6, so we can categorize our circuits in the VLSI, very large scale integration. And the last one is ultra low scale integration if the transistor count is above 10 की power 6. So by the requirement of the low power, as we discussed, by the requirement of the low power. So there are multiple reasons to aim for low power VLSI. First one is a portable device depends on the uh, first one is a trend. Changing trend, that means we are moving we are moving toward the low technology node like 45 nanometer, 80 nanometer, 7 nanometer. So we are working on the 7 nanometer, 8 nanometer. So to achieve this, so we require the low power. Next is the packing and the cooling cost because of our device or our chip generate the heat. Because of the heat, the temperature of the system or the chip will be increased. So to cool down the system, we require a packing and the cooling uh, circuits. So if we design a low power VLSI circuit so that it consume or it can generate a low heat, so it can be achieved through the low power VLSI circuits. Next is increasing of power density of the VLSI. Actually, it is the it basically calculated or the power per unit area, so it can be reduced if we are using the devices or the circuits which are consuming the low power. So basically the power density will uh, directly proportional to the design of the low power, so it can be reduced easily. So portable system, it is a handheld system like a phone, uh, cell phone, laptop. So if we want to make a portable system so that can be reduced in the size, so it can be used the through the low power design. Reliability, it is basically our system. If it is generating a low heat or and the temperature will automatically reduce and it basically the reliability of the system can be increased proportionally. So environment, if it is generating at a low heat, so our environment will be, so our design will be environment friendly. So review of the next is a review of the scaling. If you want to design any VLSI circuits or low power VLSI circuits, so this is the basic and the most important tool. We just scale down our system, so in which the all these uh, design parameters of the system is scaled down by a factor of the S. So there are two types of scaling. One is a constant voltage scaling and another one is a constant field scaling. So it basically used to provide better and faster performance and to achieve the more number of transistor per unit area. If the size of the devices is reduced, so basically we can fit more number of transistor in a single chip. So there are several drawbacks of the scaling. Increase in the leakage power, it is the main contributor in the limitation of the transistor, because when we are moving toward the low technology node around 4520, so basically the ratio of the leakage to the active power is more than the 60-70%. So basically it's around 60 to 70% is the leakage power and only we are using 20 to 30% is the active power. So in the low technology load, so we have to encounter the leakage power component and reduction in the noise margin because it is working on the at the low power voltage or low supply voltage. So the fluctuation in the supply voltage or flux or air noise may be degrade the performance of the circuits. Reduction in the reliability. It is basically because we are moving toward the low technology node. So the number of the transistor per unit is increasing. That means the heat per unit area is increasing. So the reliability of the system is reducing. Increase in the power density as discussed, increase in the temperature dependency. So CMOS technology, why we prefer CMOS technology? Because the CMOS is draws the significantly low current during the transistor from one state to another and a very little current between the transistor. So we can say the power in comparison to the BJT is very low. So low CMOS technology having is a low static power dissipation, while BJT is having high power dissipation in comparison to the CMOS technology. CMOS technology is having high input impedance and bipolar technology is having low input impedance because it is a bipolar, and there is a internal current. We say the base current. So because of the exist of the base current, it is having the low input impedance, whereas CMOS is having the high noise margin because of the robust technology, and uh, BJT is having the low voltage swing, and CMOS is having a high packing density, whereas bipolar is having a low packing density. CMOS technology having has a high delay sensitivity to load, whereas BJT is a low delay sensitivity to the load. It is having low output driving current. The basically BJT is having a two major advantage in comparison to the CMOS technology, in which first one is a high output driving capability, because in the BJT whole whole BJT whole area of the collector and the emitter is contributing to generating the output current, whereas in the CMOS technology only a small channel or inversion layer is contributing to to develop the output current. That's why it is having high output driving capability in comparison to the CMOS technology. Whereas BJT is also high transconductance, because in the BJT transconductance is directly proportional to the output current. In the CMOS, it is proportional to the root of the output currents. That's why it is basically is having a high transconductance, and CMOS is having a low transconductance. But CMOS is another advantage is it is having a bidirectional capability, whereas it is having a only unidirectional capability. So that's why the most widely used semiconductor technology today is CMOS, which is stand is complementary metal oxide semiconductor, and it is used both NMOS and PMOS transistor, where one is on while the other is off. That's why it is having a minimization in the power consumption. Compared to the bipolar technology, CMOS offer low power dissipation, high noise immunity, and high packing density, as we discussed. This makes CMOS ideal for portable and battery powered applications. Now, these are the basics. Actually, when the threshold voltage is less than gate voltage is less than the threshold voltage, that means the channel will not be created, and there is no current. When VG is equal to and greater than equal to VT, that means a low drain current is start to flow, and it would be directly proportional to the uh, applied drain voltage. When the drain voltage is equal to the saturation voltage, at that point the output current will be saturate in comparison to the output voltage. Now the overview of the power dissipation in the CMOS. So in CMOS circuits, total power dissipation comes from two major sources: dynamic power and the static power dissipation. Dynamic power arises when the transistor switch from one state to another state, and it is basically includes switching, short circuit, and glitching power, but majorly contributor is the switching power dissipation. Next, static power comes from leakage currents even when the circuit is ideal and we are not applying any clock pulse, or we are not applying any we are not applying any clock pulse. In that situation, the power mainly it could be as a static power dissipation. And static power dissipation is majorly having, there are so many various types of components, but basically we will focus on the three. First one is a subthreshold leakage, next one is a reverse bias leakage, and last one is a gate oxide tunneling current. With technology scaling, leakage power has become a dominant issue, so consuming energy even when the device is doing nothing. So that's why we have to focus on the static power dissipation. So first one is a switching power dissipation. When the inputs become slow and inputs become slow, in that case we can say the PMOS will turn on and we will charge the capacitor. So some part of the power supplies will store in the output node and some power will dissipate across the PMOS because in the on state it will be replaced by a resistance. So there will be a uh, there will be a generation of the heat. So only the few amount of the power supply will be stored or we can view to store in the output capacitor. When the inputs becomes high, in that case, PMOS will turn off and NMOS will turn on. In that case, the output capacitance will discharge through the NMOS and NMOS will replace by a transistor and some power will dissipate across the NMOS transistor. So the basically the formula of the switching power is the alpha G uh, F clock into C out and into the VDD square. Basically alpha G is a switching coefficient and F is a frequency and C is the total output capacitance at the output node and VDD is the stands for the power supply. Next one is a short circuit power dissipation when both NMOS and the PMOS are turned on. And during that time, there is a direct path between the power supply and the ground. That in that phase, we can say there is no charging and the no discharging no discharging and no charging is happening. So in that case, we can say uh, there is only the there is only we can say the power is dissipating. That means we are not using any power to store at the output node. So only we are generating the power or we are generating the heat. So it can be reduced if we are focusing on the rise and the fall time. So use of the rise and the fall time, we can reduce the short circuit power dissipation when we are going to we are supplying our clock pulse. In that case we have to focus on the rise and the fall time. If we are reducing the rise and the fall time or we are generating the ideal clock pulse, in that case we can say our short circuit power dissipation becomes very low. Next one is a glitching power dissipation. Actually basically previous stage in output can be work as a input for the next stage. It will take some time to reach at the input of the second stage. So during that phase, it may be treated as a previous output of the previous stage and it may be generate a wrong output. During that wrong output, it will fluctuate from high to low state or low to high state and during that we can say it produce a glitch of the power. So basically, we can reduce it by designing in a systematic way to our circuit so that we can reduce the glitch power dissipation. Now moving toward the leakage power dissipation, it is a reverse bias PN junction diode leakage current. So in reverse bias PN junction, actually the drain in comparison to drain and the bulk and source and the bulk will having a junction PN junction. Due to the PN junction, a depletion layer will form, and due to the depletion region, and because of the power supply we are applying to at the drain and the source and the bulk, a uh, reverse bias will generate, and due to the reverse bias generation in the PN junction, a small current may be flow between the source and the substrate and between the drain and the substrate, and it is basically equal to the reverse saturation current which is arise in the diode. So it can be reduced by applying proper bias at the bulk so that the component of the reverse bias can be reduced. Next one is a subthreshold leakage current, and as I discussed, it is the most among the leakage components we have to focus when we are going to design a wide fan-in or logic domino circuit. So sub-threshold leakage current, if the gate voltage is less than the threshold voltage, in that case there is we are not creating or we are not creating any channel, but and we are not forming there is no inversion layer or there is no channel, but still a current is flowing between source and drain because of the we are applying a supply voltage at the drain side, and because of the difference between the drain and the source equal to the power supply, at that time a small current between the drain and the source start to flow, still having threshold gate voltage less than the threshold voltage. So that means if we are not applying the wide fan in, we will discuss in the detail. If we are not applying any input, still a small current will flow, and because of this current, a charge share will be happen in the domino circuits. That's why we have to focus on the current. So it is the formula of the subthreshold leakage current. Next one is a gate oxide tunneling current. Gate oxide tunneling current is scaling. When we scale down our transistor, the thickness of the oxide is also reduced. So when we are applying a voltage at the gate or the drain, at the gate, because of the applied voltage at the gate, a high electric field may vertically may be produced uh, under the gate, and because of the high electric field, some electron may penetrate through the oxide and may be reached at the gate because we are applying a voltage at the gate, and due to this gate voltage a high electric field is producing at the between gate and the substrate. So because of the penetration of the charge carrier, and the current is basically the flow of the charge carrier, that means we can say the current will flow between the gate and the drain, and between the gate and the substrate, and between the gate and the drain, and it should be ideally zero. So we have to use another dielectric material between gate and the bulb. So now the design of the low power VLSI circuits, it can be categorized basically in the static as the power static and the dynamic. In the static, actually we can simplify in static CMOS. All the internal and the output nodes will be saved in the form of the voltage, whereas in the dynamic, all the internal node and the output node will be saved in the form of the charge. So in the static CMOS, basically in the static CMOS, it is formed in the we are saving all the voltage node, internal node, and the output nodes in the form of the voltage, whereas in the dynamic we are saving in the form of the charge. So that's why we required a timing circuit, so it can be refresh of the charge in the dynamic circuits. So it is static CMOS is also, there are two types, conventional and pseudo, and whereas dynamic is also having a conventional and the dynamic circuit. So first one is a static CMOS circuits. There are two types of conventional and there are pull-up network, and another one is a pull-down network. In pull-up network, it is basically designed using the PMOS, and whereas pull-down network is basically designed using the NMOS design. And why we use the PMOS to design the pull-up network? Because PMOS is a good source of the logic high, and it is a bad source of the logic 0, whereas the NMOS is a good source of the logic 0, or it is a bad source of the logic 1. That's why we always prefer to design pull down network using the NMOS, and pull up network is designed by the PMOS, because pull up network is used to charge up the output node, whereas pull down network is used to transfer the logic or output to discharge the output capacitance. Whereas in the pseudo NMOS, the whole pull up network is replaced by a single and PMOS, which is connected, the gate of the this PMOS is connected to the ground, and it is always turned on. So, as we discussed, is the static CMOS. It is created to allow a path exist from output to either the power source, or we can say to charge the output node, or to the ground. That means to discharge the output node. And these are the advantage of the static CMOS circuits. It is having basically no static power dissipation, and high it is having good swing, output swing or noise margin, we can say, because of the high voltage would be equal to the VDD, and low voltage would be equal to the zero. And it is very robust, and it is having wide noise margin because it is having a full swing at the output. So the limitation of the static CMOS is basically it is require number of two n number of transistor if you are designing an input gate, and it is having only inverting gates available if you because it is basically to design a NAND, a NOT. You can't design a NOR or the OR. If you want to design a NOR and or you basically require a NOT gate at the output that to convert the invert inverting to the non-inverting logic. So there are some basic static CMOS design. In the static CMOS design, if two NMOS are in series, we can simply can say it is a multiplication of the logic and represented by a bar. So F would be equal to A dot B ka bar. Here both NMOS are in the parallel, so it would be a OR logic, A plus B ka bar. In this circuit, it is A dot B ka bar, and because of this because of this inverter, it is converting A plus B, A dot B ka bar. That means NAND gate to the AND gate A dot B. There are several structure of the static CMOS. Here we can say the D dot bracket A plus B plus C ka bar. Here A dot B plus C dot D, because both are in the series, it is a dot product. Both are series, it is a dot product, but both branch are parallel to each other. So we can say it is a parallel combination of A dot B plus C dot B D ka whole bar. And it is basically the A plus B plus C plus D ka bar. So the pseudo NMOS, as I said in the previous slide, the CMOS pull-up network is replaced by a single PMOS transistor with its gate grounded. So whole pull-up network is replaced by a single transistor. That means the area is reduced by n minus one transistor. So basically in the static conventional we require 2n, and here we require only n plus one transistor. And PMOS require a double area to the NMOS, so it provides a huge margin in terms of the area. And other one, low dynamic power dissipation and less interconnect capacitance, because if the number of transistor is reading, so we basically say the number of capacitance, because each transistor is having a internal capacitance, so proportionally the internet interconnect capacitance will be reduced by margin. Next is a high noise margin and the limitation, because the output swing reduction and high short circuit power dissipation, because when it is performing the discharging, when we are applying any uh, discharging part to the pull down network, at that time it is charging also and it is providing the discharging. In that case, to achieve it basically will never be equal to zero, so it will having some output voltage, it may be around 0.1, 0.2 basically. So it will never generate a equal to zero voltage. It provide basically because of the charging through this PMOS. So there are some several examples of the using the pseudo NMOS. It is an inverter and it is a dot B ka bar. It's an NAND gate and it is a NOR gate A plus B ka bar. Next one is a dynamic power dissipation, and it is having a two types of conventional and the domino circuits. So first one is a conventional. Here we are using a PMOS single PMOS transistor and a pull down network, and another is a footer transistor. So pre-charge transistor is a PMOS and phototransistor is a NMOS. So in the pre-charge transistor, using the clock pulse, there will be a two operational phase. First one is a pre-charge phase and next one is a evaluation phase. In the pre-charge phase, when the clock pulse equal to 0, that means the output node will be charged up. And based on the in the evaluation phase, when we are applying a clock pulse equal to 1, in that case, this PMOS will be turned off and this NMOS will be turned on. Now it's up to the pull down network, and based on the input combination, this pull down network may be provide a discharging path or may not be. If it is providing a pull down, it is providing a discharging path. That means we can say the output node will discharge and we will get a logic 0 at the output node. If it is not providing a discharging path, in that case the logic logic will be high at the output node. In that case we have to retain the logic at the output, whatever is the previous one. So advantage of the dynamic circuit is the number of transistor is n plus 2, and it provides the faster switching speed because of the lower load capacitance and the internal, and this circuit is still a ratio-less circuits in case of the static. Limitation of the dynamic circuits, it's having a usually large power dissipation in comparison to the static CMOS, and it is having a charge sharing problem and skew problem. In the charge sharing problem, actually basically there are several transistor maybe in the series fashion. If a single transistor may be turned on which is near to this output node, and it because if a equal to 1 and b equal to 0, in that case maybe first transistor may be on and it may be share some charge from output node to some internal node. So that's why it is having a charge sharing problem. In the domino circuits, because to overcome this charge sharing problem, we are having a inverter along with a keeper transistor. In that case, if dynamic node, it is a DN, means DN stands for the dynamic node. If in the evaluation phase, if the dynamic node is equal to 1, in that case, it output node will be equal to 0, and once it becomes a 0, that means it will turn on the keeper transistor, and this keeper transistor will help to keep the high node high logic at the dynamic node. So these are the advantage. Operation is free of glitches as gate can make only one transistor, and faster switching speed because of the lower load, and charge leakage reduction or charge sharing reduction. The only non-inverting structure are possible because of this presence of inverting buffer and variation of overhead. So this is the wide fan-in or logic domino circuits in which the NMOS in the connected in the parallel configuration. So there are several limitations of the wide fan-in or logic domino circuits when the transistor in the pull-down network are in the connected in the parallel configuration. If a single transistor is on and all are the off, so a subthreshold leakage current may be occur. So because of the subthreshold leakage current, as I discussed, is the major contributor among the leakage currents in the evaluation network, which increase with the fan-in. As you are increasing the fan-in, the subthreshold leakage current will increase. And another one is a delay, and the variability becomes almost double as compared to the CMOS, and it is basically happening because of addition the inverter and the keeper transistor at the output node. Because of this, the variability in the delay and the power in the power and the delay increasing. So it is a major challenge in the designing of the wide fan-in or logic domain circuit, and noise immunity and figure of merit reduce as you are increasing the fan-in. So if you are designing a large fan-in domino or logic circuits, So these performance parameter may be reduced or because of the performance reduction. So we have to find a new method so that we can improve the performance as we are increasing the fine wide fanning. So complex is also a major challenge and novel techniques should be designed to overcome above this. So this there are several existing domino circuits. So existing domino circuits, there are basically two things. One is a pre-charge network and another one is a evaluation network. Using the evaluation network, we can reduce the subthreshold leakage current. We design our evaluation network in such a manner so that the subthreshold leakage current may be turned down. And another one is a pre-charge network in which actually basically keeper transistor always turn on in the pre-charge phase also when pre-charge transistor is available to charge up the node, but still it is on and it is consuming a large power. So to reduce this power component or in the pre-charge phase, a researcher is establish a network in which it turn off this keeper transistor in the pre-charge network if and it will turn on this keeper transistor in the evaluation network if it is required. Otherwise, it will not turn on the transistor. Next one, uh, conditional keeper domino circuits. Here, two keeper transistor is used. First one is a weak keeper transistor and second one is a strong keeper transistor and it is driven by a AND gate which is having two input. First one is a delayed clock pulse and second one is a dynamic node. And based on the combination of the delayed clock pulse and the dynamic nodes, it will turn on the strong keeper transistor. So in the basically weak keeper transistor, we can say it is having a low transistor size. And strong keeper transistor, basically, we can say strong means it is having a large W by L and weak is having low W by L. So it can be categorized based on the size of the transistor. Weak keeper transistor is always whether pre-charging is charging or not. But strong keeper transistor will turn on in the evaluation phase based on the requirement of the circuits. If it is required to retain high logic at the dynamic node in the evaluation, then it will turn on, otherwise it will remain the off. So basically it's depending on the combination or depending on the requirement of the dynamic node. If you require a high logic at the dynamic node in the evaluation phase, or basically if you are not providing any discharging path, in that case, it will turn on the strong keeper transistor and it will start to recharge the dynamic node if something is tearing through this pull down network with the ground. Next one is a domino footed dynamic circuits. So here diode footed domino circuits. Here two transistor is used at the footer and one transistor is used as a mirror along with this feedback transistor which is driven by the output node. So basically if a charge is shared through this pull down network. So if a charge shared through this pull down network, then a potential will develop at here and each transistor will remain off in the evaluation phase. Then in that case, it will provide a negative gate to source voltage to the transistor connected in the NMOS. And because of the negative gate to source voltage, the threshold voltage of the transistor NMOS transistor will increase because it is in the body bias effect. It depends on the voltage at the applying body. So because of the body biasing, we are increasing or decreasing the threshold voltage of the transistor, or we varying the threshold voltage of the transistor. If a transistor is having high threshold, that means it will have a low leakage current. If a transistor is having a low threshold voltage, that means we can say it will have a large leakage current. So that's why in the evaluation phase, when it is not providing any discharging path, in that case we are just uh, establishing a voltage at the source side to increase the threshold voltage so that the subthreshold leakage component may be reduced and the charge sharing problem may be reduced. But because of the addition of this transistor, the delay may be increased. When you require a discharge, when you are discharging the output node, in that case, because of this stacking effect, the delay will increase. To encounter this, we are using a mirror transistor and the M4 transistor. It is basically to provide the fast discharging. In that case, if you provide a discharging path through the pull down network. So the delay is optimizing through these transistors, M2 and the M4. Next one is a simple approach to reduce delay in domino circuits. Here a source degeneration transistor is used in cascaded with the keeper transistor. It is basically reducing the overall transconductance, because when we are calculating uh, the variation in the power and the delay, it is basically depending on the three factors. First one is the gain of the inverter. It may be, it can't be varied. And another one is the transconductance of the keeper transistor. To transconductance of the keeper transistor can be reduced easily. So a source degeneration method here used to reduce the transconductance of the circuit. So next one is a voltage comparison domino circuits. Here basically uh, the whole pull down network is disconnected to the actual output node. So here a virtual domino circuit is created to generate the output at actual output. So here we are just focusing on these two voltages, A and the B. Based on the voltage of the A and the B, or comparison of A and B, we are actually producing the desired output. So here we can see the dynamic node is associated only the Mn3 and the Mn4. That means it is connected to only two transistors. In that case, majorly the charge share will be happen because of these voltage, whereas B voltage is depending on the A and on the parallel do not connect. So it will not affect the dynamic node in such a manner in the previous case, where it is directly proportional to the pull down network. So here we are achieving high noise margin, low power dissipation, because there is a less fluctuation in the volt dynamic node, so that we are achieving a desired output and a stable output at the output node. Next one is a variable threshold voltage keeper circuit. As I discussed, the transconductance of the keeper transistor is directly proportional to the delay and the power variability. So here we are just uh, varying the transconductance based on the circuit requirements, and we are generating the bias voltage depends on the bias voltage. It is switching on or switching off the keeper transistor. And based on this switching and the switching the transistor or switching off the transistor. In the pre-charge phase, we wanted to switch off the keeper transistor. That in that case, we will apply a voltage so that it can switch off the transistor in our it reciprocally it will reduce the power dissipation or it will save the power. If we want in now in the evaluation phase, if the NMOS in the pull down network is providing a discharging path, that means dynamic node will be discharged through pull down network. In that case, we also want to switch off, so it will provide a body bias generator voltage so that it will switch off. If we require a high voltage at the dynamic node in the evaluation phase, in that case we will provide a VDD 1 voltage so that it can switch on the keeper transistor, or it can provide the it can switch on so that it can recharge the dynamic node so that we can get a stable output at the output node. But to get the combination of the VDD and VDD1, we required a complex algo. So that is the basic limitation of the circuits, because it requires a complex algo and it is very difficult to get the exact body voltage. So it can completely turn on and it can completely turn off. So that's why we focus to the next uh, domino logic with clock and input dependent transistor gate. Here, two transistors are inserted at the bottom of the pre-charge transistor and at the up of the pull down network. So based on the voltage of V0 and V1, voltage will be generated using a algo, and it is basically it will depend based on the combination of the input. So based on the combination of the input using a algo, we will generate two input voltage V0 and V1. And based of this, in the pre-charge, it will provide V0 equal to 0 and V1 equal to 1. In that case, this both pre-charge transistor will turn on and it will provide the high logic at the dynamic and low logic at the output. In the evaluation phase, now it's depend on the input voltage. If uh, a single input voltage is having a high logic, in that case V1 would be equal to 1, and in that case and V output always will remain equal to 0. So in the evaluation phase, so now if V1 equal to 1, in that case it will provide a discharging path and dynamic node will discharge through the V1 transistor and the pull down uh, and the putter network. If uh, all input are equal to 0 or we are not applying any input, in that case it will generate V1 equal to high voltage, and in that V1 equal to 0 voltage. In that case it will cut off dynamic node to the pull down network and only a single transistor will associate with the dynamic node. Only a few charge sharing will happen, because all the parallel transistor connected in the pull down network will be cut or will be isolated from the dynamic node. So it is improving the performance in the evaluation phase of the circuits, but it is again having a complex, and the sizing is also very complex. Next one, a novel method to control leakage and the noise. Here, the actual dynamic node and the output node is isolated from the pull down network. So here the dynamic node is depending only a single transistor or is connected to the single transistor, and single transistor is having a very small subthreshold leakage current in comparison to the large transistor connected in the parallel and are also associated with this dynamic node. In that case, it will provide the better or less charge sharing so that it will provide the stable dynamic node and stable output. So here, as subthreshold leakage current is reducing, in that case, it will provide a high high speed and low power dissipation. Next one is a here in the previous case, as all the circuits as we discussed, some isolate the output to the actual pull down network, and some redesign the pre-charge network, and some design the evaluation network. But here in the circuits, both pre-charge network and the evaluation network are redesigned to reduce the power dissipation in the pre-charge, or to provide the better noise immunity in the evaluation network. So here power dissipation is reduced by a large factor and noise immunity is increased by a large factor, because here pre-charge network and the evaluation network both are redesigned. So here a keeper control network is used to switch on and the switch off the keeper transistor based on the requirement of the dynamic. In the pre-charge network, after some time, because of the delayed clock pulse, it will turn on, and it will turn on. That means it will provide a high logic at the PMOS. In that case, it will turn off. Turn off. That means the dynamic node will not be charged through this PMOS transistor, and that means we are saving the dynamic power, because in the pre-charge network it is already pre-charge network is on. Now in the evaluation phase, if the dynamic node is not providing any discharging path, in that case this dynamic node this dynamic node will remain high. That means high, it output will be equal to 0, and through uh, this transmission gate, this transistor is off. That means output node will connect it directly to the gate of the PMOS transistor, and it will turn on based on the requirement of the dynamic node, and it will recharge the dynamic node, and it will retain the high logic at the dynamic node. And another factor here, it will generate a negative bias gate to source voltage, which increase the threshold voltage of the transistor connected in the parallel combination in this pull down network, so that the subthreshold leakage current will reduce proportionally as you are providing the you are increasing the threshold voltage. So here we are using a putter we are using a low threshold transistor, because to provide, in that case, when we are providing a discharging path or delay discharging path, in that case for the fast discharging we are having a low threshold, and to optimize the delay, that's why we are using low threshold voltage transistor. So now, as we discuss uh, how to use AI and the machine learning in the VLSI. So the use of the artificial intelligence, it is basically to optimize VLSI design, and particularly in the context of the wide fan-in or domino gates and their low power delay, low delay, and the sizing basically focus. So on large scale integration, one of the critical design challenge is managing logic complexity. When you are designing any VLSI circuits, so you have to manage the logic complexity, and it is a basic and to reduce power consumption and timing diagram, especially when it's come to the wide fan-in gates like OR gates with any inputs. So these gates are often integrated in arithmetic circuits and memory decades, as we discussed. So as we discussed in designing of wide fan-in or logic gates, because of the increased power consumption, higher propagation, larger area, and signal integrated. So this is where artificial intelligence can come into the picture. It is not replaced to any human designer. It is basically to optimize the design configuration with the help of the EDA tools. In the EDA tools, we are using the AI to optimize the thing. So it is basically to meet low power area performance constraint more efficiently than the traditional EDA methods alone. If we are using the EDA methods along with the AI, it will reduce the time and it will increase the productivity of the designer and the circuits as well. So AI techniques, including machine learning, reinforcement learning, and evolutionary algorithm can help us explore large design space faster and more intelligent. These methods are powerful the circuits. So these methods have proven beneficially for if you want to design a logic synthesis and placement and the routing when we are designing a layout of the VLSI circuits, timing optimizing to reduce the glitch power or to reduce the threshold leakage current. So how to turn on and turn off our keeper circuits efficiently. In that case, we are using the timing optimization that can be achieved using the AI. Power aware design, power efficient design. If we are we are sizing our transistor in a such manner, it provide a low power dissipation. Next is the design space exploration. So it's a logic decomposition in AI. So actually break what is the logic decomposition? It is basically break into smaller gates organized in a multi-level hierarchy, and it in that case minimize gate count and the delay. So basically it is used to, we can say, the uh, we are sizing a transistor in a such a manner so that we can achieve low power dissipation and the high speed and high noise immunity and high figure of merit. So AI model, particularly design trees or reinforcement learner, can suggest the best gate level structure so that we can achieve high performance. So next one is a power consumption. So power consumption in a wide gates is because of the high, as you are increasing the fan-in, that means the capacitance and the switching activity is increasing with the fan-in. So to predict the switching activity of the pre-charge network, of the keeper network across multiple scenario, it can be easily predict using the AI. So AI method or ML method can be used to select low power alternatives so that the dynamic power dissipation may be reduced if we are effectively turn on and turn off our keeper transistor so that the power dissipation can be reduced. So these are the synthesis tool which is used to design the low power. So neural network we can use to predict power consumption as we discussed by transistor sizing. Reinforcement learning we can use to size the transistor and the keeper, so provide high noise immunity, ML based power dissipation. So when we are designing a layout, we can use the ML to to generate the layout so that a small area may be reduced or area may be reduced using the machine learning. And the generating algorithm is also used to provide real-time feedback during the design and enabling iterative optimization before manufacturing, critical for biomedical application. And this is a log diagram how we use the AI and ML to optimize the power. And basically, as similarly, we can achieve high speed and the noise immunity using the neural network And the reinforcement learning, basically it is used to design or to size the transistor in the best possible way so that we can achieve high luminosity and high speed. Okay, so so another is a AI also used for the timing, because to reduce the delay and provide the high noise immunity. So basically it required timing optimization, and it will provide the most path. It will help AI and find out the most critical path in the output network or in the evaluation network, so that we can focus uh, to achieve the high speed. It will help AI help to learn from history. Actually, based on the historical timing reports, it will predict potential timing bottlenecks, and it will suggest buffer insertion and gate resizing and gate splitting. So based on the previous reports, it will suggest some insertion of the buffer or the delay element, or it may be suggest to resize some transistor, to uh, resize of the some transistor, or it may be provide we can use two NMOS in place of the single PMOS, so single NMOS, to provide the best. It may be suggest based on the previous data. So reinforcement learning can explore various configurations under the time. In a neural network, it is basically used to custom logic. So it can help to design custom logic blocks. We can explore more number of NOR and smaller OR gates to replicate large fan-in behavior. And it balance trade between the trade-offs delay and power and the area, as we discussed. Is a trade-off between the delay and the power area. It can be balanced throughout the AI and the reinforcement learning. So layout and the placement optimization is also the most important method to optimize or to achieve the high performance parameter. So to optimize the spatial arrangements of the gates and to reduce the wire length, we can use the optimization using the AI, and it also help to minimize the capacitance, and so that it can improve the signal integrate and radius. So AI will help to assist in floor planning at the time of the layout by predicting the congestion in the hotspots and the in critical paths accordingly. So as a circuit can be designed or can be achieved high performance parameter using the AI. So AI optimized wide fan-in on dominant circuits to provide leverage machine learning to overcome traditional limitation in power, noise, and the delay performance. So AI will help to predict with the along with the EDA tool. If we are using the AI along with the EDA tool, it provides the high accuracy and provide the high performance in the design circuits, and it will provide the best sizing of the each transistor so that you can get the high figure of merit in the circuit. Neural network optimize keeper, and there are basically we will use the neural network to resize or optimize the transistor. ML driven evaluation network, here reinforcement learning optimize transistor sizing for 18 to 16 bit input paths with minimal leakage. If we are increasing the fan in, it provide a optimized transistor size so that a substitute leakage current can be reduced. So neural network trained on circuit simulation can identify potential faults in domino circuit. It is also used to identify the fault so that the accuracy may be increased by 95% and reducing the testing time. It is around more than 70%. So it is basically very useful tool along with the EDA. So ML models predict potentially timing violation in domino circuits across operating operating condition and reducing verification cycles by 40%. So it is a summary. The major concern for the VLSI design, as we discussed, area, speed, and power. So all can be optimized using the AI and the machine learning. That's why we are including the AI and the machine learning in the VLSI design, because VLSI design itself is a emerging area and AI is also a emerging area. If you are combining both and you are using AI to design a VLSI circuits, it would be very grateful, and it will be time saving, and it will provide the best performance of the design circuit. So power dissipation, as we discussed, the important factor. So that's why we are focusing in the power dissipation when we are designing a domino circuit. So as we discussed, subthreshold leakage current and the noise immunity, and the speed is reduced as you increasing the fan in. That's why we are designing the wide fan in all logic domino circuits. So as we also discussed that it may be redesigning in the pre-charge and the evaluation network, and the reducing the transconductors on the keeper transistor, the uh, delay and the delay and the power variability can be reduced. So for AI ML techniques are transforming VLSI design by automating the circuits optimization, enhancing power efficiency, and improving the reliability, crucial for biomedical application. And for wide fan in domino or circuits, AI ML techniques have demonstrated 15 to 25% power reduction and 10 to 20% improved in the noise, as the previous experts is also told about some case studies of the some reputed company. They itself uh, claim that around 15 to 25% power reduction is achieved using the AIML, and 20% improvement in the environment. Also, the power time saving and the performance improved when we are using the AI methods to design a VLSI circuits in comparison to the traditional method. So basically, AI enhanced domino circuits are ideal for biomedical application because power and reliability are critical issue for the biomedical issue. So these include ECG and EEG machine, ADC tag converters, X-ray, ultrasound system, and wearable biosensors. So such device operate continuously and required precise low power circuits. So that's why we are using AI optimized design to achieve this thing. So these are the references which is used to uh, uh, making the presentation in the low power. Thank you. Pankaj sir, am
Thank
I
you,
audible?
Doctor. Yes, you are Dr. Ankur. If we can take up some questions, if anyone want to discuss anything from with the expert. Dr. Ankur, you can unshare your screen, not an issue.
Okay, sir.
Stop sharing, that's fine.
Okay, stop sharing. Okay.
Right. I think, Dr. Ankur, we don't have any questions from the audience. So we can end this session. Thank you so much, Dr. Ankur, for your time
Okay.
and for accepting our invitation. It is, I think it's
Welcome,
very
sir.
beneficial. Okay, one question is there, Dr. Ankul. Like EDA, is there any other tool for implementing? One question from Raj Lakshmi.
Like EDA, there are several EDA tools You can Cadence, Synopsys, Mentor Graphics, Comsol. There are so many EDA tools which can be used to design any VLSI circuits. So, and it is easily available. And now there is a government running a program C2S. Under the C2S, they are providing a free license free of cost, and you have to contact to the ministry regarding this, and they are providing uh, license of the Cadence, Synopsys, Xilinx. Uh, there are a lot of EDA tools, and they are providing.
I hope this answers the question by Raj Lakshmi. Praveen Kumar, what you are typing CMOS and MOSFET in details means? We didn't get the question even. Anyways,
Okay,
I
sir.
think this okay.
Okay, sir. Thank you.
Okay, one more question, Dr. Ankur.
Hi.
With the use of
Actually, as we discussed in the whole presentation, use along with the ADA tools, we use the AI and the ML, and it is basically very effective, and it provides the high accuracy, and it is very time saving, and it provides the best result. If you are if once you learn how to use AI in the EDA tools, it would be very effectively. And in the at the time of the fabrication, it is also provide the best results.
okay, I think this answers both the question. Okay, Dr. Ankur, thank you so much.
Welcome, sir. So can I leave, sir?
Yes, yes, thank you so much.